afternoon, students. I'm Chaitanya, Assistant Professor in Mathematics with the Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, as a continuum of fifth module, I'd like to discuss on the topic joint entropy. In the last class, we have started our discussion on entropy and measures of entropy. Now, I'd like to continue our discussion on entropy, and my emphasis is on joint entropy. So, it is a very good custom to make a note on the person who has introduced the information theory, especially the entropies. That is Mr. Claude E. Shannon, who introduced first time information theory, especially the measure of loss of information in the year 1948 while he was working in Bell Laboratories. And he has contributed a lot of things for communications, especially his work, A Mathematical Theory of Communication, is very acknowledged by the world. And he defined, in entropy, he defined the fundamental limits on compression needed for reliable data communication. That means, reliable data communication means while you are transforming information from one channel to another channel, the transformation should be reliable. Reliable means it should not contain any disturbances, and the loss of information due to disturbances should be at very minimum level. So, in order to make the transformation very smooth and very accurate, and to minimize the loss of information, okay, we need to understand information theory and entropies. So, in this entropies has given that for every data set, there will be a threshold beyond which, if you go on compressing the information, it leads to loss of information at high level. So, for every reliable communication, data communication, there will be a threshold beyond which we cannot compress. That is what the major thing he achieved through his work. And random variable, because we study entropies as a expectation of law of a random variable, we must recollect what is a random variable. See, when you have a random experiment R and a sample space S associated to the random experiment R, then any function x from the sample space to the real number set is called a random variable. And there are two types of random variables, namely discrete and continuous. If you are transforming discrete signal, then you will use discrete random variable. If the signal is continuous, then you will use continuous random variable. Okay, the discrete random variable will be, the graph of f signal will be like this, whereas the continuous random variable will be like this. So, and every random variable is associated with two parameters called expectation and variance. So, for every random variable, we can calculate E of x as well as V of x. If it is discrete, the E of x is defined as summation x into the probability of x. If it is continuous, we define it as x into f of x dx under the limits minus infinity to infinity. And V of x is defined as E of x square minus E of x whole square. These are the basic things that we must have a knowledge in order to proceed into the information theory about random variables. Okay, now here he has given an example of a random variable. He has taken a fair coin toss, that is random experiment, a fair coin tossed, and x represents random variable such that x maps the head and tail, head to the number 1 and tail to the number 0. So this is a random variable defined on the sample space associated with toss a coin, toss it for one time. A random experiment, tossing a coin for one time. Okay, so this is an example. Now, let us understand the concept of random variable into a little deep level, because we must be able to calculate in entropy, we must be able to calculate E of x and V of x. So first let us try to understand what is E of x with an example. Here we are considering an experiment that throwing a pair of dice at a time. This is our experiment. When you throw a pair of dice at a time, generally there will be two numbers appearing on the faces of the two dice. So now he is defining the random variable x as x of a comma b is equal to maximum of the two numbers that appear on the pair of fairy dice. That is, x of ab is equal to maximum of a comma b. This is what he defined the random variable. Now for this random variable, he is asking us to calculate the expectation v of x and the variance v of x. Okay, let us try to find them. Yes. So, two dice are thrown at a time. That means the random variable, the sample space will contain total outcomes 6 into 6, that is 36. Because 2 dice means 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6, 6 are 36 possibilities are there. That is why I have written the number of elements in the sample space will be 36. Let us list out those 36 elements. I am going to construct those 36 elements as a 6 by 6 matrix, that is 1, 1, 1, 2. The first row will be the elements, the pairs starting with 1, that is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And the second row, I am going to write the pairs which starts with 2, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. And the third row starts with 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. The fourth row will be 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. The fifth row will be 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. The sixth row will start with 1, that is 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So these are the 36 pairs that will occur when you throw a pair of dice. Okay. Now I am going to construct another set, that is, I am going to denote it as max S. Max S is nothing but selecting maximum number from each and every pair of the set S. So here the maximum will be 1, in this pair the maximum will be 2, and the third pair 3, like that, 4, 5, 6, 2, the maximum is 2 here, and among these two the maximum is 2, here the maximum is 3, then the maximum is 4, the maximum is 5, the maximum is 6, and here the maximum is 3, here the maximum is 3, here the maximum is 3, 4, 5, 6, so 4, 5, 6. Proceeding to the next row, the maximum of each and every bracket, maximum is 4, 4, 4, 4 and 5, 6. In the fifth row, the maximum will be 5, 5, 5, 5, 5, 5. In the last row, the maximum will be 6, 6, 6, 6, 6, 6. So the maximum of S, max S is nothing but a 6 by 6 matrix or 36 element set, which is resulted like this. Now, after constructing the max S, I'm going to calculate the probabilities of different possible outcomes under random variable X. So, for that, I'm going to write first, what are the possibilities under the definition of x of a comma b is equal to maximum of a comma b when a pair of dice are thrown? The possibilities are nothing but getting maximum 1, getting maximum 2, getting maximum 3, getting maximum 4, getting maximum 5, getting maximum 6. So I'm going to calculate P of 1, which represents getting the probability of maximum as 1. Getting the number 1 as the maximum when a pair of dice are thrown. That will be, how many ones are here in this set? Only one. So only one favorable outcome. But total outcomes 36. Similarly, probability of getting maximum 2. That means when a pair of dice are thrown, what is the probability of getting? The highest number 2 is, how many 2s are there? 1, 2, 3. So 3 by 36. Probability of getting the highest number on pair of dice when they are thrown is 3. Is like this. That is 1, 2, 3, 4, 5. So it is 5 by 36. And the probability of getting maximum as 4, the number should be 4 when a pair of dice is thrown, is like this. That is 7 by 36. The probability of getting maximum as 5 is like this, 9 by 36. And the maximum getting 6 is 11 by 36. So, we have calculated the 6 possibilities. We have calculated the probabilities for 6 possibilities. The first possibility is getting, when a pair of dice are thrown, getting maximum 1, getting the number maximum 2, and getting the number as maximum 3, and maximum 4, maximum 5, maximum 6. We got the probabilities as 1 by 36, 3 by 36, 5 by 36, 7 by 36, 9 by 36 and 11 by 36. After calculating these probabilities, I am going to build a table called probability distribution table. Okay, in this table, I'd like to write first row as the x values, that is getting the maximum, that is 1, 2, 3, 4, 5, 6. Next, I am going to write the probability of getting x, that is probability of getting maximum 1 is 1 by 36, this is 3 by 36, this is 5 by 36, this is 7 by 36, this is 9 by 36, this is 11 by 36. Now I am going to calculate E of x. E of x formula is summation x into P of x. That means x1 P1 plus x2 P2 plus x3 P3 plus x4 P4 plus x5 P5 plus x6 P6. Because there are 6 elements, 1, 2, 3, 4, 5, I have written x1, x2, so on, x6 and their probabilities. Nothing but 1 into 1 by 36 plus 2 into 3 by 36 plus 3 into 5 by 36 plus 4 into 7 by 36 plus 5 into 9 by 36 plus 6 into 11 by 36. See here, you can take 1 by 36 common, then you will get 1 plus 2 plus 3, 1 plus 6 plus 15 plus 28 plus 45 plus 66. That is equal to 111, 131, 139, 154, 160, 161. Okay, so 161 by 36, and the answer is it will be around 4 point. Okay, 144, 170 again 4.4 something like that, or 4.5 you get. So what is the expected value for this experiment? That is around 4.5. We can assume between 4 and 5 you are as expected. So many number of times or majority times you are expecting that the maximum will be either 4 or 5. That's what you are telling from this. Okay. Now I am going to calculate E of x square for the sake of V of x. So in order to calculate E of x square, we have to build one more row here. Squaring the first two, that is 1 square 1, 2 square 4, 3 square 9, 4 square 16, 5 square 25, 6 square 36. After building this, E of x square will be summation x square into P of x. So we can write 1 into 1 by 36 plus 4 into 3 by 36 plus 9 into 5 by 36 plus 16 into 7 by 36 plus 25 into 9 by 36 plus 36 into 11 by 36. So after doing this, 13, 56, 9 5 is 45, 57, 58 and 112, that is 170, and 250 means 225, that is 395, and 360 means 450, 650, and it's almost around 700. You can estimate 700 with that. This is E of x. Then you can calculate V of x as the formula E of x square minus E of x whole square, which is nothing but 700 by 36 minus some number 161 by 36 whole square. So this is how we will calculate expectation and variance for a given random variable. Okay. Now, after understanding this example, okay, we'll proceed to the calculation of one more problem we'll see at the end as an example. Okay. So now we are going to the details of entropy and joint entropy. Entropy is the measure of the average information content missing from a set of data when the value of the random variable is not known. That means when you have a set of data like x1, x2, so on, xn, and there is some content is missing, like some second column or fourth column like that, entropy measures how much amount of information you are missing when a set of data is available with you. That means you would express the amount of information you are missing in a specific number, and that number is called entropy. So entropy is nothing but measure of loss of information, how much amount of information we have lost. It helps to determine the average number of bits needed for storage or communication of signal. What are the benefits of entropy? There are two benefits. By calculating entropy, you will come to understand how much storage you will need to store the available information. Okay, that means you know that this amount of information is missing. That means you will be available with this amount of information. So to save this amount of available information, how much storage I have to allocate, that you can easily assess. Okay. Second thing, you can determine a threshold beyond which if you go on compressing the signal, it will lose the essence of info. It may cause a loss in the essence of info. That means if you go on compressing beyond that, you will lose the real essence of information and it will be of no use. So there are two benefits. As the number of possible outcomes for a random variable increases, entropy increases. That means when the range set is high for a random variable x, okay, then automatically entropy will be high, because when there is a high number of random variable images means you are having a huge data set. When you have a huge data set means you will have when you have to lose much information. When you are compressing, definitely you have to lose high amounts of information. That means the entropy is always directly proportional to the cardinality of the range set of x of s. That's what this point is saying. As entropy increases, information decreases. That means if the entropy is big number means the loss of information is more. That means the available information is less. That means available information is always inversely proportional to entropy, and entropy always directly proportional to the cardinality of range set of the random variable x of s. Okay. So we can apply these entropies in so many things in the daily life, where MP3 compressions like video compression of MP3, MP4 videos, and photographs compression, that is JPG format photographs, PNG format, zip files. You may send files in the form of zip folders, and while compressing them, you may lose some essential information. So you can control that by using entropy. Okay, and cryptography, while encoding and decoding data, you may lose some important things to be delivered. You can control them with the help of entropy. And signal transmission across a network through email or text message or cell phone, there are also the loss of information, valuable information can be controlled with the help of entropy. So these are the major applications that we come across in our real life on entropy. Okay, now what is the measure of information? How the entropy is defined? Let us look into the details. So first of all, see, when you have a random variable x from a sample species to real numbers. Okay, this random variable is defined on the data set of communication of the information which you have to analyze. Okay, and assume that this sample space is discrete. That is, s is equal to s1, s2, so on, sn. Okay, then you can calculate log base 2 of probability of si. Definitely, because probability is a number between 0 to 1, and if you multiply with minus, it will be positive. So this means it's a measure of information. Okay, that's the lead for defining entropy. And you know that the sum of all probabilities is always 1. Okay, and a small p of si means more information. Okay, and as it was unexpected or surprising. Okay, that means surprisal he's telling. Surprisal means with less probability. Then we call less surprise and more information. That's what you understood. And entropy is defined as E of log P of S, or E of log X, you can say. E of log X. So entropy is defined as, that means you can understand it as summation minus probability of getting Si into log 2 P of Si. This is what we call entropy. This is what we call entropy. Okay, where I is equal to 1 to n. Okay, this gives us a specific number, positive number, that tells how much amount of information we are going to lose in the compression. Okay, under the channel H. This is called entropy of H. Okay, so by using the channel H, where H follows probability function P of X. Okay, by using the channel H while communicating the information, you are going to lose this amount of information on an average. And if you go on beyond this level, you will lose the essential information. That means communication will be totally out of use. Okay, so it produces lower bound on number of bits needed to represent the information with code words. Okay, next, you can see an example alphabet of transforming A. The probability of A transforming as A is 0.4, probability of transforming B as it is 0.6. And by using the definition, E of H, or entropy of H, is summation P of Si log P of Si with a minus here. Okay, by using this definition, you can calculate this as minus 0.4 log 2 0.4 plus 0.6 log 2 0.6, and you can calculate, you are going to lose on an average 0.97 bits of information. Okay, 0.97 bits. If you go on beyond compressing this level, you will lose the essence of information. Okay, so maximum uncertainty occurs when all possibilities are equal. Generally, if all probabilities of are equal, okay, of S, of the sample space S, which is related to the channel communication H, then definitely you will get maximum uncertainty. Okay, because entropy will be very high, and hence maximum uncertainty. Okay, there are different kinds of entropy, measures of entropies. First one, Shannon's entropy, which is defined nothing but Pi into log Pi, I is equal to 1. We have very well known and very popularized entropy that we generally come across. Okay, and binary entropy is nothing but minus P into log P. You know, P denotes success and Q denotes failure. Then this is the formula, P into log P, Q into log Q. But you know that success is always negation of failure. That means 1 minus failure, and failure is equal to 1 minus success. This, you know, because P plus Q is always 1, P is equal to 1 minus Q, Q is equal to 1 minus P. So by using that, binary entropy is defined with the simple formula, P into log P plus 1 minus P into log 1 minus P, which is multiplied with minus outside. And in continuous case, the differential entropy is defined as integral minus infinity to infinity f of x log f of x dx. Okay, so these are the different important entropies that we use in real time. Okay, next. Properties of entropy. As I already told you, entropy is nothing but expectation of log of expectation minus log of P of x, because it is defined as summation P Si into log P Si with minus. Automatically, you can understand this as this expectation of negative of logarithm on P of x. Okay, now it is not function of variable values, it's a function of the variable's probabilities. Yes, here we are defining entropy as P of Si into log P of Si. That means it is not on Si's, it is on P of Si's. That is what it is saying. Usually we measure the information in bits, but we measure loss of information in nats, which is based log base 2 is called nats, and log base 10 is called Shannons. Shannon means log base 10. Like that, there are several based on the logarithm, based on the difference in the logarithm, different measures are called. Generally, we use nats because natural log or base 2, because binary means 0, 1. So, generally, we use log base 2. Okay. Now, what is joint entropy? Our today's discussion is on joint entropy. We are defining joint entropy of two random variables x, y as h of x, y is equal to expectation of minus log p of x, y. That is equal to summation minus p of x, y is equal to log of p of x, y. So this is a joint entropy. That means when you use two channels x, y at a time, how much amount you are going to lose. Okay. To calculate this, we define joint entropy, which is denoted by h of x, y, which is defined like this. Okay. Now, when you define it like this, okay, you can also define conditional entropy. Apart from joint entropy, you can also define conditional entropy as h of x given y. Okay, which is something but expectation of minus log p given y, which will be product of p of x given y into log of p of x given y, and the whole product will have a minus sign. Okay, this is what conditional entropy. Okay, now, so what is joint entropy? Joint entropy is nothing but the common loss of information when you are applying two communication channels at once to communicate the information. It is defined as h of x, y. It is denoted by this, and it is nothing but corresponding products of the probability with the logarithm of the probability of x, y. Okay. And they are summed and multiplied with minus, then you will get a positive number that is called joint entropy. Okay. Now, you can subtract joint entropy and the entropy of second variable, that is y, and you can calculate the condition probability, that is conditional entropy, that is what this is. That means conditional probability is nothing but joint entropy minus the entropy of y. That's what it says. Mutual information is nothing but suppose you have a random variable x and you know the entropy of x, how much information you are losing through using the communication channel h, which is following the random variable capital X, and you know the condition probability h of x given y. Okay, then the mutual information can be calculated with the help of the formula I of x, y. I means information, that is why I of x, y means information of x, y, which is nothing but the difference of h of x minus h of x given y. So this is mutual information. Okay. Now, entropy and mutual information, I already defined what is entropy. Okay, and I have already defined joint entropy, which is nothing but p of xy into log p of xy. Okay. Now, we already defined conditional entropy, and we have seen the relation between conditional entropy minus the conditional entropy, and the general entropy minus conditional entropy will be the mutual information. That is what we understood. Okay. Now, here you are writing p of y given x is equal to x. Okay, y given x is equal to x means, see, I could write it as summation p of x, or you can go to the I of x, y. This, okay, I of x coming, this is what we have to find. For that, that would be summation of lambda is equal to 1 to some number, and lambda is equal to some number 1 to n p of x, y log p of x, y divided by p of x into p of x. So here what you are observing, the common probability, joint probability divided by the product of individual probabilities. This gives the mutual information, another formula for mutual information. Already we know this formula, but we can also directly calculate with the help of probabilities by this direct formula. Okay, and also by the use of symmetry, you can also observe that these are same, h of x comma x minus h of x by y, and h of y minus h of y given x both means same, both reads same answer. Okay. So finally, what we observed, I of x comma y is equal to h of x plus h of y minus h of x. Okay. This is a third representation of formula without using any conditional entropies or what. This is the most simplest formula that we come across. Then, okay, so the information is nothing but h of x plus h of y minus h of x comma y. If you want to calculate information of x with itself, that is that means h of x plus h of x, okay, minus h of x given x. This will be cancelled and the answer will be h of x. That is what we are saying. Okay, now so joint entropy is nothing but under the continuous case. So far we discussed discrete case. In the discrete case, the joint entropy is defined as summation p of x comma y log p of x comma y, where x and y are discrete values. But now under continuous case, joint entropy is defined as summation x and summation y with a minus. This is joint density function f of x comma y. This is log of density function log of f of x. So this represents continuous case, and the previous definitions represent the discrete case. So in both the case, you are trying to calculate the joint amount of information that on average to specify the value of two discrete terms. That means the joint information we are going to lose, the amount of information we are going to lose, that is h of x. Okay. So in the same way, you can define conditional entropy also, just by replacing f of x comma y with f of y given x. Okay. Entropy measures the amount of information of a random variable or the length of the message required to transmit the outcome, and the amount of information in two random variables. Conditional entropy is the amount of information in one random variable given we already know the other. Okay. This is what the difference between entropy, joint entropy, conditional. Entropy means it is a measure of information of a random variable, okay, or length of the message. Joint entropy means amount of information lost in two random variables. Conditional entropy means the amount of information in one random variable given that already another random variable is known. Okay. Now you can see joint entropy in a simple way like this. H of x is equal to summation p of px of x is into log px of s. Okay, and this is the formula. Okay, this is the general entropy, normal entropy, and joint entropy is nothing but summation p of x comma y log p of x. Okay, you can see a small problem here. You are doing that, tossing one coin at a time or two coins at a time. You are getting 0 tails or 1 head. 0 heads, 1 head. 0 heads, 1 head. Then if you denote like that, y is on one coin, x is one coin. You will get the probabilities like this. Getting 0 means 1 by 4. Getting 1 means 1 by 4. All heads 1 by 4. All tails 1 by 4. And 1 head means 2 by 4. That is 1 by 2. Okay. 0 heads means 0. Okay. That in this way we have found the matrix, and we calculate h of x comma y by using this formula. H of x comma y by using this formula, if you calculate, it becomes like this. Okay. Now, in the same way, we can extend the joint entropy to the entupled random variables as h of x1, x2, so on, xn as summation of probability of happening x1, x2, so on, xn simultaneously with the logarithm of probability of x1, x2, xn. Okay. Now, you could see what happens between the entropy of our entuple. Okay, this is the relationship wherever you go, this valid. Okay, now just have discussed what is conditional entropy. H of y comma y given x means h of x comma y minus h of y. So from this this is positive, this is positive. That is why you can understand that h of y given x is always less than or equal to h of y. Now we will prove that h of y given x is something but h of y. So what happens? So we got h of the conditional probability as general probability. H of y given x is nothing but h of y, because p y given x is p of y, automatically x y will be independent, hence we will get this as h of x comma y. For the case of entropy, the inequalities, famous inequalities of probability follows, that is, are valid. That is, h of x dot h of y is equal to less than or equal to h of x dot y less than or equal to h of x plus h of y. So this is an important relation. And also h of x given y x comma y is equal to h of x plus h of y given x. Okay, so one equality we can observe here, and this is always non-negative. H of y given x is always non-negative. That means every entropy is always non-negative, and h of y given x is always less than or equal to h of y. H of y is always given or equal to h of y. Okay, and h of x comma y given z can be also written as h of x given z plus h of x dot z. Okay, like that we can understand what is the conditional entropy and joint entropy. Okay, so this is the reference through which you can find more information about entropies and joint entropies. With this, I'd like to conclude my lecture for today. In the next lecture, we'll meet on some more interesting topic on entropies. Thank you for your patience. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.